Welcome to another deep dive. Today we're taking a look at the fascinating world of shapes and space, but more specifically, how we understand those things through the lens of numbers.
Yeah, numbers and shapes. It's a powerful combination.
It is. Our listener sent in a whole bunch of stuff on coordinate geometry, focusing on straight lines.
Straight lines, the foundation of so much in geometry.
Exactly. And our mission today is to break down all this material about straight lines and make the core ideas really clear and engaging for you guys listening in.
We want to make it easy to grasp regardless of, where you are in your math journey.
Yeah, like a shortcut to understanding these fundamental geometric ideas, but through their algebraic representations.
Algebra and geometry together. Now that's where things get interesting.
It is, and this whole idea of combining algebra and geometry, that really took off with René Descartes back in the 1600s.
1637, to be precise. His book, La Géométrie, was a total game changer,
It was. It showed how we could describe curves and shapes using equations.
Equations. It opened up a whole new way of thinking about geometry. It wasn't just about visual stuff anymore. It became something you could analyze and really play with algebraically.
Absolutely pivotal moment in math.
Definitely. It's amazing how much of what we do today stems from that work.
Now, before we get too deep into straight lines, let's quickly go over some of the basics that this material kind of revisits things you've probably seen before.
The building blocks, so to speak.
Right. We're talking about the coordinate axes, that x-axis running horizontally and the y-axis vertically, and then that grid they make, which we call the xy plane.
Right, and how we use coordinates to pinpoint locations on that plane by plotting points.
Yes, plotting points like giving every location its own unique address.
Precisely. And then there's the distance formula for finding how far apart 2 points are.
And the section formula for dividing a line segment into specific ratios.
All essential tools for working with lines and anything built from lines.
Exactly.
Yeah.
So let's picture this. We've got our XY plane ready to go.
Okay.
How do we give a specific address to a point on this plane?
Okay, good question. So let's take the point 6, 4 as an example. What's the story behind those two numbers?
The 6 and the -4, what do they tell us?
Well, the first number, that's 6, tells us the horizontal position, how far to the right the point is from the y-axis. In this case, it's 6 units to the right.
And the -4.
It's our vertical position, so it's telling us to go 4 units down from the x-axis because it's negative.
Got it. So 6, 4, 4 means 6 units right and 4 units down.
Exactly. Now, if we had a point like 3, 0, it would be 3 units to the right of the y-axis.
And right smack on the x-axis itself because the y-coordinate is 0.
Exactly. Neither above nor below the x-axis, just right on it.
So it's like every point has its own unique GPS coordinates.
A precise way to pinpoint its location.
I like that, a math GPS. And once we have these coordinates, we can do some really cool stuff, like figuring out the exact distance between any 2 points.
Right. How far apart are they? That's where the distance formula comes in.
So if we have point P with coordinates by 1, y1, and point Q with coordinates by 2, y2, how do we find the length of that straight line PQ connecting them?
Okay, so the distance formula, it might look a bit scary at first, but it's actually based on something really familiar, the Pythagorean theorem.
Pythagorean theorem. Now that takes me back.
It's all about right triangles. Remember, A plus B equals C star.
Right, where C is the hypotenuse, the longest side.
Exactly. So with our 2 points, P and Q, think of the horizontal distance between them, that's by 2 minus by 1.
And the vertical distance is y2 minus y1.
Right. Now, if you picture those as the 2 shorter sides of a right triangle, the distance PQ is the hypotenuse.
Ah, I see now. So the distance formula PQ equals the square root of by 2 minus by 1 squared plus y2 minus y1 squared is just the Pythagorean theorem applied to coordinates.
Exactly. It's a beautiful connection between algebra and geometry, and it lets us calculate distances precisely.
Let's try it out. We want to know the distance between our earlier points, 6, 4, and 3, 0.
Okay, so plugging those into the distance formula, we get the square root of 3 minus 6 squared plus 0 minus -4 squared.
Which simplifies to the square root of 9 plus 16.
And that's the square root of 25, which is just 5.
And it says 2 points are exactly 5 units apart.
Exactly. See, it works.
Now, what if we have a line segment like that one connecting our points P and Q, and we want to find a point on that segment that divides it into 2 pieces with a specific ratio?
Ah, that's where the section formula comes in handy. It's like slicing a cake. Precisely.
So how does that formula work?
All right, so if a point divides a line segment joining PI1, Y1, and QI2, Y2 internally in the ratio MN.
So M and N are like the proportions of the 2 pieces.
Exactly. The coordinates of that dividing point are given by this, it's a bit of a mouthful, but N-COF1 plus MX2 divided by M plus N for the X coordinate.
Okay, so we're kind of combining the x-coordinates of the endpoints using the ratio.
Right, and the y-coordinate is ny1 plus my2 divided by m plus n, same idea, but with the y-coordinates.
Combining them based on the ratio.
Precisely. It's essentially taking a weighted average of the x's and y's.
A weighted average, that makes sense.
Let's illustrate this with an example. Say we have points A1 at us 3 and B 3 and 9.
And we want the point that divides segment AB in the ratio 1.3.
Okay, so plugging those values into the section formula we get, 3 times 1 plus 1 times 3, divided by 1 plus 3 for the x-coordinate.
And for the coordinate,
We have 3 times -3 plus 1 times 9 divided by 1 plus 3.
which gives us 0 over 4 for the x-coordinate and 0 over 4 for the a-coordinate.
And that simplifies to 0, the origin itself.
So the origin divides that specific segment in that specific 1.3 ratio.
Exactly. It's all about finding that perfect dividing point.
And there's a special case of this section formula that's really useful. What happens when the ratio MAN is 1.1?
Ah, yes, that gives us the midpoint formula.
The midpoint, so the point right in the middle of the segment.
Right, and its coordinates are simply the average of the x-coordinates and the average of the a-coordinates.
So by 1 plus by 2 divided by 2 for the x-coordinate.
And y1 plus y2 divided by 2 for the a-coordinate.
A simple way to find the center.
Very handy. Now, before we move on to lines themselves, there's one more formula we need to revisit. How do we find the area of a triangle if we know the coordinates of its 3 corners?
The area of a triangle based on just its coordinates.
Right, so if the vertices of a triangle are by 1, y1, by 2, y2, and by 3, y3, the area is given by 1/2 times the absolute value of a big expression.
The B expression.
It's by 1 times y2 minus y3 plus by 2 times y3 minus y1 plus by 3 times y1 minus y2, all inside that absolute value.
Okay, so it's a systematic way to calculate the area, but it definitely involves a bit of careful calculation.
It does, but it works. Let's try it with an example. Say we have a triangle of vertices 4, 4, 3, 2, and -3, 16.
Plug those in and see what we get.
Okay, so plugging those into the formula, we get 1/2 times the absolute value of 4 times -2 minus 16 plus 3 times 16 minus 4 plus -3 times 4 minus 2.
A lot of numbers in there.
Let's simplify it step by step. So inside the absolute value, we have 4 times -18, which is -72, plus 3 times 12, which is 36, and then -3 times 6, which is -18.
So it's 1/2 times the absolute value of -72 plus 36 minus 18,
And that all simplifies to 1/2 times the absolute value of -54.
which is just 1/2 times 54, 27.
So the area of that triangle is 27 square units.
27 square units, all from just the coordinates.
Now, remember how we talked about if that area calculation ended up being 0?
What does that tell us?
It means the 3 points aren't actually forming a triangle at all. They all lie on the same straight line.
Ah, because a flat triangle has no height and therefore 0 area.
Exactly. So a 0 area means the points are collinear.
Okay, that's a really important point to keep in mind.
It is. Now, are we ready to dive into straight lines?
Let's do it. And when we talk about representing a line algebraically, one of the most fundamental concepts is slope.
Slope. It's all about how steep the line is.
So how exactly do we define slope?
Well, think about a line sitting on our coordinate plane.
That good old XY plane.
Right. Now, this line, it makes an angle with the x-axis. We usually focus on the angle made with a positive x direction measured counterclockwise, and we call this angle the inclination of the line.
The inclination, so it's like how much the line is tilted.
Exactly. And this angle, it always falls between 0 degrees and 180 degrees.
So horizontal lines, they have an inclination of 0 degrees.
Right, they're flat.
And vertical lines are straight up at 90 degrees.
Exactly. So the inclination captures the line's orientation.
Got it. So how do we get to slope from this inclination?
Well, the slope, which we usually represent with the letter m, is defined as the tangent of that inclination angle.
The tangent as in like cosine tangent?
Yep, that's the one. So m equals tan.
Okay, so m equals tan, but there's a catch, right?
Yes. This definition only works when length isn't 90 degrees.
Because a vertical line doesn't really have a defined slope. It's infinitely steep.
Precisely. Tan 90 degrees is undefined, so we say the slope of a vertical line is undefined too.
But for all other lines, we can use m equals tan.
Exactly. And think of tan as just a way to measure how tilted the line is. A small angle means a gentle slope, and a larger angle means a steeper slope.
So a horizontal line with an inclination of 0 degrees has a slope of 0 because tan 0 degrees is 0.
Right. 0 slope means completely flat, no rise over run.
But for a vertical line, we can't really use that ratio idea of rise over run because the run is 0.
Exactly. It's undefined.
Okay, that makes sense. Now, what if we don't know the inclination angle directly, but we do know the coordinates of 2 points on the line?
Yeah.
How do we find the slope then?
Ah, good question. So if we have two different points, let's call them P with coordinates by 1, y1, and Q with coordinates by 2, y2, on a non-vertical line.
Non-vertical, because those vertical lines have undefined slopes.
Right, we can calculate the slope m as the ratio of the vertical change to the horizontal change.
Rise over run.
Exactly. So m equals y2 minus y1
Right.
divided by 2 minus by 1.
So the change in y over the change in x.
Precisely. And this formula works whether the angle is acute or obtuse.
Acute meaning less than 90 degrees and obtuse meaning greater than 90 degrees.
Right, it all comes back to that right triangle picture, remember?
PQ is the hypotenuse.
And the slope is just the length of the vertical side, that's the rise, divided by the length of the horizontal side, the run.
It's really intuitive when you think about it that way.
It is. It's a way to quantify the line's steepness just using the coordinates.
Okay, so we've got a good grasp of how to define and calculate slope. Now, what does the slope tell us when we're comparing two different lines?
Ah, good question. So let's start with parallelism. What's the relationship between the slopes of two parallel lines?
Parallel lines, those that never intersect.
Right, so two non-vertical lines on our coordinate plane, they're parallel if and only if their slopes are equal.
If they have the exact same steepness.
Exactly. Same rate of rise over run, they'll never meet.
Makes sense. If they're tilted the same amount, they'll always maintain that same distance between them.
Precisely. And conversely, if two lines have the same slope, they're parallel.
Because their inclination angles must be the same.
Right, within that 0 degree to 180 degree range.
So same slope means, same direction means parallel.
It all connects.
Now, what about when two lines are perpendicular to each other? What's the connection between their slopes in that case?
Perpendicular, that's when they meet at a 90 degree angle.
A right angle.
Yes. So for two non-vertical lines to be perpendicular, their slopes have to be negative reciprocals of each other.
Negative reciprocals. What does that mean exactly?
It means if one line has a slope of m1 and a second line is perpendicular to it with a slope of m2, then m1 times -2 equals -1.
Okay, so their product is -1.
Exactly. Which also means that m2 is equal to -1 divided by m1.
They're flipped, and one is negative.
Right. Think about it visually. If one line is going upwards to the right, a perpendicular line is going downwards to the right or upwards to the left.
So their slopes have opposite signs.
And the reciprocal part comes from that geometric relationship of the angles changing in a way that their tangents multiply to -1.
Okay, so perpendicular lines have slopes that are negative reciprocals of each other.
It's a key relationship.
Let's put all this into practice. Our listeners sent in a bunch of examples. And the first one, example 1, is all about calculating slopes in different scenarios.
Sounds good. Let's see what we've got.
So part A asks for the slope of a line passing through the points 3, 2, and Lineca 1, 4.
All right, using our trusty slope formula, m equals y2 minus y1 divided by 2 minus by 1.
So we plug in the coordinates.
Right, we get 4 minus -2 divided by -1 minus 3, which simplifies to 6 over -4.
Which is -3 over 2, or -1.5.
So the slope of the line connecting those points is -1.5.
Part B gives us a line through the points 3, 2, and 7, 2.
Okay, so for this one, we have m equals -2 minus -2 divided by 7 minus 3.
Which gives us 0 divided by 4.
Which is just 0, a slope of 0.
Then a slope of 0 means we're dealing with a horizontal line.
Exactly. Which makes sense because the y-coordinates of both points are the same -2, so there's no vertical change, no rise.
Okay, that's part C is a line passing through 3, 2, and 3, 4.
Okay, so m equals 4 minus -2 divided by 3 minus 3.
That's 6 divided by 0, division by 0.
Which means the slope is undefined.
Just like we talked about with vertical lines.
Exactly. And notice that the x-coordinates of both points are the same 3, meaning it's a straight up and down line.
No run, just rise.
Right. Part D of this example is a little different. It asks for the slope of a line that has an inclination of 60 degrees with the positive x-axis.
So we don't have coordinates this time.
But we can go straight to our definition of slope, m equals tan.
Since slope is 60 degrees, we need to find tan 60 degrees.
Which is the square root of 3, so the slope of this line is exactly 3.
Approximately 1.732.
Right. It's a steeper line.
Okay, we've got a good handle on slope. Now, what happens when two lines intersect at an angle? How do we find that angle using their slopes?
Okay, so if we have two non-vertical lines with slopes m1 and me2, and their inclination angles are a1 and a2 respectively.
So we're talking about the angles they make with the positive x-axis.
Right. The angle log between those two lines can be found using this formula. Tan equals the absolute value of m2 minus m1 divided by 1 plus m1 times m12.
A bit more complex than just the slope formula.
It is, but it's important to remember that absolute value, it gives us the acute angle between the lines, the smaller one.
Because two lines crossing actually form two pairs of opposite angles that are equal.
Right, and those adjacent angles, they add up to 180 degrees. They're supplementary.
So if one angle is E, the other one next to it is 180 degrees minus this.
Exactly. Now, our material has a good example. Example 2, it says the angle between two lines is 4 radians, which is 45 degrees.
And we know the slope of one line is 12.
And we need to find the possible slopes of the other line, right?
Exactly. So how do we approach this one?
Okay, let's set m1 equal to 12, and let m2 be the unknown slope we're trying to find.
And ev is 4 and tan 04 is 1.
Right. Plugging those into our formula, we get 1 equals the absolute value of m2 minus 12 divided by 1 plus 12 meter 2.
Okay, so now we have an equation with m2 in it.
And because of that absolute value, we actually get two possibilities.
Two possibilities, how so?
Well, either m2 minus 12 divided by 1 plus m22 equals 1, or that same expression equals minus 1.
Because the absolute value of both 1 and meta 1 is one line.
Exactly. Now, if we solve the first equation for meta 2, we get meta 2 equals 3.
And solving the second equation gives us meta 2 equals meta 13. So there are two possible slopes for the other line that would give a 45-degree angle with our line of slope 12.
Right. It makes sense geometrically a line can intersect another at a specific angle in two different ways.
Like one slanting upwards and the other downwards, but both making the same angle.
Exactly. Now, example 3 brings back the idea of perpendicularity. It says we have a line passing through natus 2, 6, and 4, 8.
And this line is perpendicular to another line passing through 8, 12, and x 24.
And the challenge is to find the value of x.
So we've got some detective work to do.
All right, let's break it down first. We need to find the slope of that first line, the one passing through natus 2, 6, and 4, 8.
Using our trusty slope formula.
Right, so m1 equals 8 minus 6 divided by 4 minus natus 2, which gives us 2 over 6, which simplifies to 13.
Yeah, for the second line.
We have the points 8, 12, and x 24. So its slope meta 2 is going to be 24 minus 12 divided by x minus 8.
Which simplifies to 12 over x minus 8.
Now we know these two lines are perpendicular, so the product of their slopes must be minus 1.
M1 times M2 equals minus 1.
Right. So 13 times 12 over x minus 8 equals minus 1.
Okay, let's solve for x.
We can simplify that equation to 4 over x minus 8 equals minus 1.
Then multiply both sides by x minus 8 to get rid of the fraction.
That gives us a 4 equals negative x minus 8, which we can distribute to get 4 equals minus plus 8.
And rearranging that gives us x equals 8 minus 4, so
Okay.
x equals 4.
We found our missing x coordinate.
All right, now our listener's material also talks about the condition for 3 points to be collinear. We touched on this earlier with the area of a triangle.
Right. If the area is 0, the points are collinear, but we can also express this condition using the concept of slope.
How's that?
Well, 3 points. Let's call them A, B, and C. They're collinear if and only if the slope of line segment AB is equal to the slope of line segment BC.
So they have to have the same steepness.
Exactly. If those two segments share a common endpoint, in this case B, and they have the exact same slope, they got to be on the same line.
They can't veer off and still have the same slope at that connecting point.
It's like a train staying on its tracks.
Okay, and example 4 gives us 3 points, PHK, QS1, Y1, and RX2, Y2, that are all on a single line.
And the task is to show algebraically that this implies the condition h minus by 1 times y2 minus y1 equals k minus y1 times by 2 minus by 1.
A bit of a mouthful, but let's break it down.
All right, so since PQ and R are collinear, the slope of PQ must equal the slope of QR.
Because they're all on the same line.
Right, so the slope of PQ is k minus y1 divided by h minus by 1.
And the slope of QR is y2 minus y1 divided by 2 minus by 1.
Now, if we set those two expressions equal to each other, we get k minus y1 divided by h minus y1 divided by 2 minus by 1.
Equation with fractions.
But we can easily get rid of those fractions by cross-multiplying.
But we multiply both sides by h minus by 1 and by 2 minus by 1.
And that gives us exactly the condition we were trying to show. H minus by 1 times y2 minus y1 equals k minus y1 times by 2 minus by 1.
So that equation is just a restatement of the idea that the slopes have to be equal for collinear points.
A nice connection between the algebra and the geometry.
Example 5 brings in a real-world application, a time and distance graph that shows an object moving in a straight line.
Okay, so we're seeing how these ideas can be used to model real-world situations.
Exactly. We're given 2 data points on this graph at time t equals 0. The distance d is 2.
So the object starts 2 units away from some reference point.
Right. And at time t equals 3, the distance d is 8.
So it's moved farther away.
And the goal is to find the law of motion, basically the equation that tells us how the distance d depends on the time t.
All right, so how do we use our knowledge of slope to figure that out?
Well, since the motion is linear, we know that any 3 points on this line have to be collinear.
So if we take any other point on that line, t's d, along with our two given points, 0, 2, and 3, 8, they must all lie on the same straight line.
Meaning the slope between any two of those points has to be the same.
Right. Let's calculate the slope between 0, 2, and 3, 8. That's 8 minus 2 divided by 3 minus 0, which is 6 over 3, which is 2.
So the slope of this line is 2.
Now let's consider the slope between 3, 8, and t. That's d minus 8 divided by t minus 3.
And since those slopes must be equal, we have the equation 2 equals d minus 8 divided by t minus 3.
Right. Now to solve for d, we can multiply both sides by t minus 3.
That gives us 2 times t minus 3 equals d minus 8.
Which we can expand to 2t minus 6 equals d minus 8.
And finally, rearranging to get d by itself, we have d equals 2t plus 2.
So the law of motion for this object is d equals 2t plus 2.
And that slope of 2, what does it represent in this context?
That 2 is the speed of the object, how much the distance changes for every unit of time.
So it's moving at a constant speed of 2 units per unit of time.
Exactly. We've successfully used slope to describe this linear motion.
Okay, we've explored slope thoroughly. Now let's move on to the different ways we can express the equation of a straight line.
There are quite a few standard forms, each with its own advantages.
So let's start with the simplest ones, horizontal and vertical lines.
All right, so a horizontal line, it's all about having a constant y value for every point on it.
So no matter what x is, y is always the same.
Right. And if a horizontal line is located at a distance, a units from the x-axis.
A is like how far above or below the x-axis it is.
Exactly. Its equation is simply y equals a if it's above the x-axis.
Y equals a if it's below.
Right. For vertical lines, it's the x value that's constant.
So if it's a distance b from the y-axis,
We have x equals b if it's to the right of the y-axis.
and x equals me if it's to the left.
So these are the simplest forms because one of the variables is always fixed.
Example 6 asks us to find the equations of 2 lines that are parallel to the axis and both pass through the point, make us 2, 3.
Okay, so for the line parallel to the x-axis, its y-coordinate will always be 3.
Because it has to pass through, I get 2, 3, and be horizontal.
Right, so its equation is simply y equals 3.
And for the line parallel to the y-axis,
Its x-coordinate will always be minus 2.
so its equation is x equals minus 2.
Exactly. Simple and straightforward.
Next up is the point slope form. This one's super useful when we know one point on the line and its slope.
As the name suggests.
Exactly. So if we have a non-vertical line L with slope m and it passes through the point x0, y0, what's its equation?
The point slope form tells us it's y minus y0 equals m times x minus x0.
Okay, so we're using the slope and that known point to describe the line.
Right, and this form comes directly from the definition of slope.
If we take any other point, xy, on that same line, the slope between xy and our fixed point, x0, y0, has to be equal to m.
Right, so y minus y0 divided by x minus x0 equals m, and rearranging that gives us the point slope form.
It all connects back to that fundamental definition.
It does. Now, example 7 asks us to find the equation of the line passing through minus 2, 3 with a slope of minus 4.
So we have our point and our slope.
Perfect. Using the point slope form with x0, y0 equal to minus 2, 3, and m equal to minus 4, we get y minus 3 equals minus 4 times x minus 2.
Which simplifies to y minus 3 equals minus 4 times x plus 2.
Which we can expand to y minus 3 equals minus 4x minus 8.
And if we rearrange that to the standard general form, we get 4x plus y plus 5 equals 0.
There's our equation.
What if we know 2 points on the line, but not the slope directly?
Then we can use the 2-point form.
Which sounds like it uses 2 points.
It does. So if a line passes through 2 distinct points with coordinates by 1, y1, and by 2, y2.
2 known points.
Right. Its equation is y minus y1 equals y2 minus y1 divided by 2 minus by 1 times x minus by 1.
Okay, so we've got those coordinates in there, and look at that fraction.
y2 minus y1 divided by 2 minus by 1. That's just the slope formula.
So this 2-point form is really just the point slope form, where we've replaced them with the slope calculated from our 2 points.
Exactly. It's all connected.
Example 8 asked for the equation of the line passing through the points 1, 1, and 3, 5.
Okay, plugging those into the 2-point form, we have y minus 1 equals 5 minus 1 divided by 3 minus 1 times x minus 1.
Which simplifies to y plus 1 equals 6 over 2 times x minus 1.
Or y plus 1 equals 3 times x minus 1.
Which expands to y plus 1 equals 3x minus 3.
And rearranging that into general form gives us 3x minus y minus 4 equals 0.
Another form down.
Another one. Now let's talk about the slope-intercept form. This one's a favorite because it tells us the slope and where the line crosses the y-axis.
So we get 2 key pieces of information right away,
Exactly. It's y equals mx plus c.
where m is our old friend, the slope,
And c is the y-intercept, the y-coordinate where the line intersects the y-axis.
which happens when x equals 0.
Right. giving us the point, 0, C.
And there's another version that uses the x-intercept, isn't there?
Yes, it's y equals m times x minus d, where d is the x-intercept.
So the point where the line crosses the x-axis is d0.
Makes sense.
Example 9 tells us that tan equals 12, meaning the slope m is also 12. And we need to find two lines with this slope, one having a y-intercept of -32 and the other an x-intercept of 4.
Okay, so two different lines, but both with the same slope.
Right, so for the first one, we have m equals 12 and the y-intercept c equals -32.
Plugging those into y equals mx plus c, we get y equals 12x minus 32.
Which we can rearrange to get rid of the fractions.
Multiplying everything by 2 gives us 2y equals x minus 3.
Or in general form, x minus 2y minus 3 equals 0.
Now for the second line, we have the same slope, m equals 12, but this time the x